We're going to start off now with, and welcome to our presentation on advanced design, a collaboration between Stitcher Circuits and Bread. My name is Soren. This is my fourth year at FRC. I'm a senior at my school, and I am the hardware design lead for Team 1678.
I'm City. This is my third year on the team. I'm a junior in high school, and I'm the design lead on Team 5940.
A quick outline of what we're going to go over are some motor selection, applications to springs and gas shocks, some materials that you'll be going over, weight savings that you can have, an optimal drivetrain setup, and ways to prevent mechanical issues. Oh, next slide. The first thing I'm going to go over is motor selection. Next slide. Now, motors come in many different shapes and forms, each with their own pros and cons. And each has different unique variables which allow it to do different things on the robot. The first thing is stall torque. This is the maximum amount of torque that a motor can output at zero velocity. It's useful for deciding on gear ratios, but the current draw peaks can allow breakers to trip and can damage motors, given that this is a very high stress thing to test. Motor draw is exactly this. As torque demand increases, so does the current. Knowing what your draw on each motor is allows you to prevent things such as brownout on your motors and damage to your electronics. The next thing is move time. This is how long your mechanism takes to move from one position to the next, and this depends on speed, torque, or the gearing on your robot. Last thing are motor curves, which is much like what you have here. It compares your power, your speed, and your torque for every motor, and the sweet spot that you're looking for is right at the center, where efficiency and reliability are right at its best. Next slide, please. Now, how do you go about deciding on these motors? Each of them has different ratios to decide on, but again, they're not all the same. Not only do you have to look at what are these motors able to do, but they each come in different sizes, such as the Kraken, although very powerful, with 1,100 watts, is also much larger than things such as the Kraken X44. And they each have different applications, such as on the chart above, you can see that the Kraken X60 is by far the most powerful motor above the rest. Yet, when you're looking for efficiency, for things with lower torque, things like a sim are better for things such as flywheels that don't require as much torque. Next slide, please. Now, how do you go about organizing these motors? Because when you pick a motor, you also have to consider the application in which you're putting it in. There are many things that contribute to which motor you decide on. One, the motor type. Two, what gearing you're choosing to use. And thirdly, what mechanism you're putting on. Having this organized is very important to making sure that you have a motor that supports the speed you want for your mechanism and that your robot has enough current to power that. Next slide, please.
All right, now I'm going to go over the applications of springs and gas shocks. The next series of slides will be on this. Next slide, please. Okay, so to go over constant force springs, I'm going to go over how a normal spring works first. So when you think about how a spring works, the first thing that comes to mind is the Hooke's law, and that's the force that the spring can exert is equal to the spring constant multiplied by the displacement of the spring from equilibrium. So what does this mean? It means that when you extend or compress a spring, it gets harder to compress and it gets harder to pull apart. And this just means that the force that the spring exerts, it's not a constant number, but it linearly changes as the displacement changes. And this is great, like this non-constant number. It's great if you're just storing energy or if you're just absorbing shock, and if it's not catered for like a specific geometry. But in many cases, systems require for like this constant spring force, and that's where constant springs come in. And what they help do is more like smoothly lift, per se, like arms. And I have a example in the next slide for this. Okay, yeah. So the first thing I want to go over of this example are gas shocks. Gas shocks basically, instead of having like coiled wire that like move closer and further apart, they have compressed gas, which stores energy. And allows the mechanisms that it's connected to counterbalance its weight based off of the spring. So it provides nearly constant force, not perfectly constant force, which basically allows, like, if you see over here, this is the pivot. So this is the pivot, and it's connected to the carriage of the elevator. And here we have like a very heavy mechanism on this carriage, which was the elevator. Which was the shooter. This is from 2024. And having this gas shock helped counterbalance some of this weight. You can think of it as like a heavy lifter. So it really helps like the motors that's spinning the pivot of the shooter to take less load. And they're compact, they're self-contained, and they're very low maintenance, so they're easy to switch apart as well. Oh, something I forgot to mention, they also slow down at the end, so they're great in like elevators and such. Constant force springs, I'm sure many of you guys have seen applications of these in elevators, and it's designed to roll out like a measuring tape, and the force is almost constant across its like entire range, and it's usually used in elevators, as you can see. Again, it helps counterbalance like the weight of the carriage. If you were to just imagine the idle position to be like the measuring tape, the constant force spring to be fully rolled up, it has a tendency to try and shoot up, which helps, again, the motors from not drawing too much current. Okay, moving on to torsion springs. Torsion springs store energy through bending and rotating instead of compressing and stretching. So what does this mean? This means that the force that the spring exerts, the torque that the spring exerts is proportional to the angle that it's stretched at. And you can see this applied in like, so instead of like a normal spring compressing and folding back, it resists turning in certain directions. And they're used mostly in things like climbers. We use that in our 2025 robot because it helps it like latch back on. Again, so these are just, springs really help efficiently use your motor power. Is there anything else? Yeah, so these are extension springs, what I've been referring to normal springs for all this time. These follow Hooke's, I've not been saying this slide. These follow Hooke's law, and they're proportional to the displacement that the spring sees. They provide a pulling force, they return to normal position, just like a normal spring. And they're great to use in like latches and such, which is what a lot of teams did for their climber. Next slide.
Alright, so I'm going to go a bit into materials. Now, next slide. As we're going into each year, it always seems tough to get under that weight limit. And a great way to actually do that and to have good mechanisms that are both light yet are maneuverable are through picking more lightweight materials. Two of these first primary ones are SRPP and carbon fiber. Now, SRPP, two types of this are called twill and mass composite. They're both very often in a flat stock like this, and although it's difficult to mill, it is possible, especially with twill, which is just several stacked layers of SRPP, while mass composite is SRPP layered with solid SRPP. Now, these can both be combined to create way more lightweight, yet also very structurally sound mechanisms. For example, this was the end effector from this year. It combines both of these using SRPP just as a flat stock, which, although it's tough, it is also able to move and allow the algae to slot in well, while using carbon fiber, which is much more rigid and durable, all the while being lightweight. It keeps the separation of the wheels, also allowing the algae to stay within its slot without getting out of the rim. Now, using materials such as this, you're able to make things that are structurally stable, yet for a mechanism that moves as fast as this, going up and down an elevator, it's really important to use lightweight materials that can really withstand the acceleration. Next slide. Another use of materials is filament types. There are so many to choose from, and each one has a different use to them. A few of the most common I'll go over are PLA, ABS, PETG, TPU, and Onyx. These are ones that we very commonly use on my team. And first off is PLA. It's very easy to print, and it produces a very smooth and detailed part. The difficulty is that it is a bit brittle, and it definitely deforms easily in heat. As for ABS, it's very similar to PLA in that it deforms easily in heat, but that's not quite true for Petchy, which is what we use most commonly since it is tough, although a bit flexible. It is very resistant to moisture and impact. On the opposite side, we have TPU, which is a very almost squishy material because it's very flexible and impact resistant, but it can be difficult to print due to the fact that it's soft and has a tendency to jam. However, this can be used for things such as the inside of our rollers this year. It allows us to have that bit of compression that you need for game objects to pass through. On the opposite end of that is Onyx. This is very tough. It's stiff and very heat resistant with an excellent finish. The difficulty with it is that it's expensive and it requires a hardened nozzle to print. But when it does print, it can make very solid parts for your robot. Next. All right.
Okay. So the section's about weight savings, and this is something we find ourselves focusing on quite a bit during the on-season. So yeah, these are just some ways that we have done that. Okay. Starting off, we do a lot of pocketing on our robot, and this just basically means that taking off certain materials, like some amount of material, off of your plate to make it a lighter part. And the thing is, like, an unpocketed part will always not be as strong. An unpocketed part will always be stronger than a pocketed part. But what the goal is with pocketing is to retain most of the strength in in areas of the plate that take like the most load and the most stress. So it's kind of like a trade-off that you have to think about making, like how much weight can you save while still maintaining like the structural integrity of your mechanism. There's something called like partial pocketing, half depthing, and that basically means instead of going like fully through with your pockets, you can go like some fraction of the plate depth. So if you're working with like, let's say quarter aluminum, you can go like eighth instead of fully through. And yeah, this helps like save some of that like torsional rigidity. Yeah, but it also helps save weight. Something that we haven't done much, but we'll probably start doing in the on-season is using really thick stock, but pocketing it quite a bit so that it doesn't weigh as much, but it's really torsionally strong. And yeah, this is just a really good way to have not too much material and have it not weigh as much, but still be very rigid. Yes, consider thinner tubing. So our go-to is usually like 16th tubing, but, oh, next slide. But considering thinner tubing, our go-to is usually 16th tubing, unless like the system requires rigidity. And by system, I usually just mean like drive-based and drivetrain tubes, because obviously that takes a lot of impact. Robots like directly ram into it. So yeah, we like keeping those tubes 8th, but everywhere else, like our elevator tubes, any other like non-essential tubes, we try to make sure that they're 16th, because tubes do weigh a lot. Yeah. Oh yeah, and with thin tubes, we try to make sure to add like a lot of good reinforcement with like gussets and things like tube plugs. Next slide. And plates. So there were 2 ways to go about this. Considering thinner plates to begin with. So there are times, I'm sure we've all faced, where we wanted something more rigid than, let's say, 8th aluminum. Usually we just default to like using quarter, but sometimes that just weighs too much, and we were looking for an alternative, and we just decided that we could start using 3/16 aluminum instead. So that's just like a very nice middle, because like it's 16th off, but it does save us quite a bit of material if like we follow the trend and yeah, make sure that's constant. And heavily pocketed thicker plates, I think I mentioned that already. And yeah, this is one of the examples of using not quarter aluminum, but this is a B-bot that we're working on. It's not at this competition, but these are gussets made out of 3/16 aluminum instead of quarter aluminum. And we thought that this would just be enough to retain the elevator and support it, because it's on all 4 sides, and we have like CF tube at the back to reinforce it. Okay, and 3D printed wheels. If you guys remember, started talking about Onyx, that's something we use to print. So these are the WCP injection molded hubs for the new Swerve, for the Swerve XS. And we started trying these in the on-season, and we really needed to cut weight. And we saw that if we just printed these hubs out of Onyx, we saved like about 0.2 pounds per wheel, which accumulated to like almost a pound overall. and that's honestly a pretty huge number during like when like every pound counts. So this is like just a random thing that we found helped. Yeah. Next slide. Smaller bearings. In mechanisms with shafts that don't see too much radial load, we try not to use like big radial bearings. Either we try to size that down to use like not like 1 1/8 like OD bearings, but smaller. And if possible, we try to use dead axle instead. And we did that in our end effector because we know that these shafts are not seeing an incredible amount of load. And if we were to just swap them out with a smaller ID shaft, and that would help our bearings, as you can see, like, well, you can't see them, but they're nested in the pulleys, the gears, and that would make it so that the bearings are smaller because bearings weigh a lot. And yeah, that's also a weight savings method that we do quite a lot. Yeah, this is from our 2025 plot. Next slide.
All right, we were talking about drivetrains earlier, and next. There are many options for drivetrains this year, and the first part are the many types of bumpers that are available. The two I'll highlight are wood bumpers and metal bumpers. One example of a wooden bumper setup they could make very quickly are with just pool noodles with a wood backing. These are attached with a plate which has a bolt and nut going through, which can be taken off reasonably quickly with a ratcheting wrench. It is cheap and very simple to make, and it can be made multiple times with reasonable ease. On the other side are metal bumpers. These are much more difficult and expensive to make. They have layered foam with a backing of a very thin sheet of metal, I believe like 90 thou thick, 90 thou to about 1/4 of an inch. They are instead attached with nut plates, as you can see in the diagram below. The positioning that has over the wooden bumpers, which is really nice, is that you can take an impact driver and you can quickly dismount the nuts and take off the entire bumper. They also, although very difficult to make, have proved to be very durable throughout the season. Another strategy for bumpers is things such as bumper spray or coatings, which allow the bumpers to have less friction against game objects that come in. Like this year, we had the algae, which has caused many difficulties to robots. Having a bumper with less friction, less possibility for tipping over, is great for a year with game objects such as this one. Next. And swerve drives. This is the next part of drivetrains. There are so many types. Of course, you still have tank drives, which are much easier to make. Swerve drives are more difficult to code, but they're more customizable, and there's many more opportunities with them. First off, they vary in many sizes. Some, like the MK5 right here, are small and compact downwards. You also have ones where the motors are on top. But the way that they're customizable is you can change things such as the ratios to model after your cycles for the optimum cycle time. You also are able to change your wheels, such as the hubcaps, as mentioned before, or changing your tread. Two examples of tread are your tread wheels and your molded tread. Molded tread, it is surprisingly durable, yet it only comes as one stock. Tread wheels, you can cut out of large pieces of tread, but they do run out faster. Other things you could do with swerve drives is you can have them both an encoder to tell in which direction they're pointed, and mounted on them you can also have covers which keep the grease inside. There are many modifications you can make to swerve drives, and which ones you choose can change how your robot functions. Next. Preventing mechanical issues. Next. Now, this happens a lot, and it's very important to make sure that you're properly documenting what you're doing with your robot to make sure that it's ready for every match. The goal for mechanical checks is to have the robot as physically ready as possible to perform well in matches and just during meetings. We will do this during meetings just so that software is able to run code that's reliable, that isn't impacted by mechanisms, and definitely before every match during competitions. It's important that you have, or it's helpful that you have a mechanical checklist for things to point out on the robot, because you might have a too much turnaround. You might have a very small turnaround. It's important to know what to look for first. A few good ways to do this are to note the key failure points on each mechanism and make sure that each match you're checking through those. A few ways we do this is through well, I showed on the next slide, I believe. Yeah, here's a checklist. There you
Okay, great. So this is a checklist that we have in our pit that we use, and yeah, I'll just go over some of like the details. So there's a example of like a snippet of the checklist here. The first thing that we write up there is the match number. So if anything goes wrong and if we need to like look back to any match, we can easily like flip through the pages. Oh yeah, and these are like in paper copies at our pit, just because like we like having other things on our like monitor screen. And yeah, so the first thing we document is the match number. The second thing we have is all of the checks. They're grouped by subsystems, and I think that's similar to how you guys do it,
Yes.
right? Yeah. So and we have a way for like, so we have certain people who are mostly like kind of assigned to check certain subsystems, and they have to like sign off with their initials. So if something does end up going wrong with that specific subsystem after the match, we just talk to the person who was in charge of checking it and ask them what they saw and if there was anything that looked like it might potentially fail. And it's labeled high, medium, and low priority in the checklist. And if there were any potential breaks that pit crew doesn't know, like if there aren't like mechanism heads there, they try to look for them and try to talk to them, like say like, oh, this plate looks like it's cracking, do you think it's going to be an issue? And things like that. Yeah, and having like a break log is just so important. We keep like a running one for every comp, and we like either like going through it the day of the competitions or going back and looking through it and just noticing like any trends or patterns and things we can do to fix it so it doesn't happen again at another competition. And yeah, each person needs to sign off, like I mentioned before. Is there anything else like that?
Yeah, we have a very similar system. It's very important to track what goes wrong in the competition. That's the best way to make sure that you're able to get back at that as fast as you can, fix the issue, and move on. Like we call it fail faster. We just make a list of everything that went wrong, and then by next competition, we make sure someone is assigned to make sure it goes right next competition. So a few of some specific checks you can make to keep your robots maintained and performing match after match are one, if you're using swerve drives or any other gearbox, make sure you're having that greased every 1 to 2 matches to make sure that your gears, although they spin very fast, they can wear quickly if they don't have any grease to hold them apart. Same goes for swapping tread. Depending on which one you use, they can wear down. It's always nice to have 1 or 2 spare at a competition because it can impact both performance during teleop and also reliability during auto. Other things you could do such as are IP on rollers or other surfaces which you want more slip or more hold. As you're going on the field, you have dirt from the field, you have dust from the game elements when they're shredded by robots. It goes in your rollers and it can impact your performance. IPA or other clean substances are a great way to make sure your robot is in good condition to continue intaking and cycling pieces. Another great thing that we do on almost all of our primary bolts are just bolt security check marks. They are just aligned with a paint pen, so we don't have to individually check every bolt. We can just see if that line is still intact. We know that it is secure. If it is not aligned, such as that image right there, we know that the shaking of the robot or its rotation has caused it to slip out. It needs to be brought back in. In addition to just making checks, you can't always account for everything. No matter how much you tune your bolts or prepare your robot, another robot's going to run into yours, you're going to have issues. That's why it's always good to design for serviceability. Make sure you know, and you'll learn this as you're going through the season, you'll see which parts break every other day. Make sure that those parts are both easily accessible. That should be something that you're considering in your design. How is this going to be assembled, and how can this be taken apart? If it's difficult to take apart, that's something you should be taking account of. For example, this intake, because it was 2024, it would break a lot of the time. And that's why we have three bolts right there. You could just take off the intake and swap on a new one. On that point, if you're able to, having another mechanism or even just spare parts of the mechanism that break the most, such as points where the intake pivots on or the rollers themselves, are great to have an extra or spare for because anything can happen at a competition.
I like to mention something here. So agree with most of those points. On our robot this year, our end effector had like a history of failing a lot and during the on season. And so we always kept like a hot swappable version. Like I don't know if you guys see, but like if you come by our pit, we have this like spare end effector always on us. And I think that's really helped us like just have like a full set of spares, everything with the hardware, belts, pulleys, everything. And something else that we know fails a lot. So just like finding specific things that on your robot that you know fail a lot. Like our intake pulleys, are this like specific intake gear that grinds down a lot. We make sure to have like multiple sets of spares for those specific things because obviously you don't want to be limited after you go to competition by just like a few factors.
Next
Sorry.
slide.
Yeah.
All right. Before we go into questions, could you guys all quickly fill out the survey? And we'd be glad to answer any questions you guys have about design or this presentation. Right. Once you guys are done, we'll be glad to take hands on any questions or curiosities that you have about advanced design.
Great.
I guess my question would be like, how are you budgeting testing parts and like going, how thin can we go?
Wait, sorry. Like how thin can we go?
Like, how are you budgeting it and going like, we can only spend this much on parts, so like, when do you stop testing and go, this is as far as we go?
Oh, like do you mean like during the off season, like prototyping?
What's the
Yeah.
cutoff between like spending money on testing and building the robot?
Mm-hmm.
Is there like a certain limit?
I don't think we have more of like a timeline than
Yeah.
like
Because for our team, it's a cost thing.
oh
It's
yeah,
not-
costing. Okay, yeah. Yeah, well we make this like Gantt chart at the start of the season
Mhm.
and we have like everything mapped out. Like we need so we make 3 robots during the on season. We make Alpha, which is our first robot. The goal with that is to just like get something that can interact with like the game elements of the robot, and we just hand it off to programming because we really want to get them started on that. And then we work on Beta, which is our competition robot, but just like a little worse. We call it our like practice robot. It's made out of like mostly metal. Alpha has like a lot of wood on it, and Gamma is like our competition robot. It's everything has to be precise. But to answer your question, we basically map like each of like the robots like completion stages on this, and for us, we stop testing when we start nearing like the end of that period. If we know that Alpha needs to be done by next week Saturday, by like this week we really should be like nailing down on like a design to put on Alpha. It really doesn't have to be perfect at this point. It just needs to be something that can work and can interact with like whatever the game piece is, and like hand off and do like the basic robot tasks.
So what I'm getting is for you, it's not we don't have the parts. It's not going to come here in time.
Yeah.
It's we have all the parts. How long do we have to play with it?
Yeah, the time is like the expensive
Yep.
bit. Yeah.
Something else we do to answer your question, just do as much testing as cheaply as you can before you commit to something.
Mhm.
Yeah.
Is before we'll actually make a mechanism, the first week or two will just be prototype everything you can think of. We will have we'll section people off into different groups. We will have 6 or 7 different prototypes running at the same time,
Sure.
seeing what works, and then we'll try multiple of a thing that works until we find something that we think is reliable enough to finally send.
I think, yeah, totally makes sense. If like material is a limitation at some point, like I think going in and looking at past games for similar game pieces and like trends, I think has definitely helped. It's getting kind of difficult because like the game design committee is coming out with like interesting game pieces, but it's always possible to go look back at like old games and looking at like the winning designs and things like that to kind of get an idea to prototype things. Also build blogs of other teams, they're really great like resources because then you can like skip some stages of testing. A lot of like our robot has like heavily inspired off of some build blogs things that we saw from teams, so that's definitely a way to save material and time. Does that answer your question?
Kind of.
Okay.
In terms of pocketing, do you do like simulation on it beforehand, or just kind of eyeball it?
We don't actually do like that much simulation. A lot of pocketing. This sounds almost wrong. It's kind of like half vibes and like half you think about like the load path, and if a part looks like really strange, we just like run, like, you know, the on-shape simulation.
Yeah.
We like running that and just seeing like the points with like the most load, and we try to just keep like more material there. So it's just like it puts like infinite amount of like load there. So it's not really simulating. So no, we don't actually do that.
Because it's tough to tell exactly how much load is going to be on any given part,
Yeah.
but you can see what piece of that part is going to break first. That is where simulations come in useful. Yes.
I wanted to ask, like, your design schedule, I guess. Like, how do you have time for iterations and, like, just, like, 3 robots before the competition season?
It is a lot of time. But it's also a lot of planning ahead of time. Once you know what you're going to do, you have again, it's a lot of delegating too. Some people don't have all the numbers to have people do things individually, but if you try to get people to, for example, we have the groups of people working on each mechanism. We split the work as much as we can, so we can keep iterating as fast as we can.
Yeah, similar things. I think setting up like a timeline that you kind of force yourself or force your team to follow is really, really helpful, because it really and you map out like the competitions that you're planning on going to, and you map out like software handoffs. Like, I want software to have the robot by this week. Having like that kind of tight schedule really helps, because then your like mindset of like, I need to get this done by this time changes. And again, yeah, just like put in the hours of like, some days you finish prototyping, you have to go home, you have to CAD like another prototype, test it again. You just spam like, you know, testing and iterating on it. Delegating definitely helps. So having people trained in the off season. So training people on how to like do basic CAD things, prototyping, which is something we're actually doing right now. We're getting our freshmen to like do some basic prototyping on like wood, and just like getting into that mindset really helps, because then you have more hands to help, and people who could be doing more important things like, I don't know, coming up with the architecture or something like that can be doing that, and people who are just trained to prototype can also just be pulling their weight. Yeah. Does that answer your question?
Yeah, thank you.
How do you go about collaboration? And I guess communication as well during the design phase, because I know for us it's often hard to like make sure that a lot of people are doing the right thing when you're designing. And how do you go about splitting up the designs into different subsystems and making sure that everything works together?
Well, first off, in terms of splitting it into different subsystems, we will, of course, have our most veteran members, of course, working on these robots. But then, along with our better members, we'll have someone more junior, who doesn't quite have their bearings on it. But by having them involved in that process, they'll be able to do better next year. And for making sure that they're all staying on schedule, during the design phase, we'll do continuous design reviews very often. We'll have them send out what they have, and then I will review them. I'll help them with their designs. And then during the assembly stage, we have use Slack, so we have them post on a channel called like Robot Status, and they will update us on where the robot is and what needs to be done next, so we're on the same page of what we need to do.
Yeah, we do like similar things as that. We put a lot of importance in design reviews, because that's where like most of the design communications happen. Like, so in the beginning of all season, right, like the design head decided that we needed to prototype like XYZ mechanisms, and they delegated to like the veteran members who know how to CAD. And so yeah, that happens, and then there's a design review process, and that's just to make sure that any like mistakes that can be avoided before the assembly process are like they're addressed, so that it doesn't like slow down the prototyping process itself. I wanted to mention something else. Forgetting. Oh yes, and we have these things called build blogs that and this is just like a channel in like our Slack workspace. And what we do is that every mechanism that's been prototyped, the subsystem head, who's usually CADing the subsystem, they take a video of that and they post it in build blogs, and they write the things that they tried, like the variables that they had for this prototype and what they're planning on changing. And in this, maybe they'll like tag the people in their subsystem group. This might be just like underclassmen, and they'll tag like the design head. And so yeah, from there, that like allows the person responsible for like the main assembly, so that's the design head, to be in the loop with everything. So that definitely helps like, the communication aspect. Just yeah, talking about it. Does that answer your question?
Yes.
Great. Yes.
In one of your slides, you were talking about checklists, and you had high, medium, low priority checks.
Yes.
So I'm wondering, what does that mean? Does that mean low priority checks may not get done because you run out of time, or?
Okay, so low priority checks, I think a better way to say is like best practices checks. Like, they don't usually, like, it's not something that we'd expect to fail, but it is something that we would like to check if we have the time. So anything that we know is critical, that not even like at the brink of breaking, but at the risk of being damaged, that's our high priority checks. And that's in like the really tight, like the 4 match turnarounds, we like checking those at the least. And the low priority checks might just be things that just we haven't seen break, but things that should be checked. So like these might be like bolts, and actually I don't know, I'm not on Fit Crew myself, but
Okay.
yeah, mostly like best practices checks.
Oh yeah, this is a little bit specific, but when you were talking about bumper mounting, you were saying that like the wooden bumpers you tend to use like the plates, and then metal tends to use like the nut plates, right?
Yeah.
Is there like any particular property of like the materials that makes these specific mounting methods like better, or is it kind of just like that's typically what people do?
That's what my team is. What's your team done in terms of bumpers?
We haven't tried the metal bumpers. We usually just use wood. And have you guys seen like the WCP mounting, the bumper mounting method? So it's just like a bolt, and you just put a nut on top. It's like a L flange that is attached to the bumper, and when you put it on, you just put a nut on top. I don't know. We just haven't tried anything else, and this works for us. We like wood screw the L plate into the bumper, and if you ever have to change it out, it like wears down the wood. So I think that's just one thing that is not so good about wood. But yeah, metal bumpers, they're probably, I'm assuming they like last longer and stuff.
Yeah, they're
Yes.
tougher and more expensive to make. But
They
do
are
last
more
longer.
expensive. They probably take more time, but alright. But mounting, we just do that one thing.
Oh yeah, there's no one way to make bumpers. Like you said, you had wooden bumpers, but it also had that nut that can come out really quickly.
Yes. So we can have that. I think it just depends on how you mount the plate to the wood.
Yeah, so mixing and matching the best parts of bumpers is a really great way to go. Alright. Any last questions? Alright. Thank you, everybody.